Yes, perfect. Thank you, Dan.
All right, great.
So just in case you missed that really nice intro that Prabal gave, I am the chief engineer / scientist of JPL. Lori Leshin actually works for me. I have a direct phone line to President Biden. No, I'm Rob. I'm a little peon at JPL. Thanks again for letting me invade Goddard today. Really appreciate it. So I'll be talking about preparing for the next generation of space telescopes. I work on two major projects at JPL that sort of dominate my time card. One of them is Roman Coronagraph, and the other one is Exoplanet Watch. So I think most of you know about exoplanets in the room, but just in case we have some interns on the line or in the room, the two methods I primarily use for my own research are the transit method, and I think actually, can I move that? So in the room, you're going to get presenter mode, sorry. Yeah, but if I do it the other way, it shows it the other way for people. So we'll just do that. There we go. So one of the methods I primarily use is the transit method. This is if you're looking at a host star, if you're super lucky, that host star will have a planet orbiting around it. If you're even luckier, the geometry will be just right, where the planet will pass in front of the star, blocking out the star's light, causing the star to dim a little bit. And this method is really useful because the amount of light dim is going to be telling us how big the planet is relative to its host star. Bigger the planet, more dip in light, smaller the planet, less dip in light. And this method is also extremely powerful because it enables us to study the planet's atmosphere. Not only does the optically thick portion of the planet's disk block out the star's light, but also that small annulus of atmosphere around the planet as well. So we can actually observe how the planet's atmosphere absorbed the star's light. And from that, we can use Beer's law, not drinking IPAs, but actually analyzing the light of the exoplanet itself and how it scatters and absorbs the host star's light to then sort of figure out what the planet's made out of. And the transit method has been extremely useful and powerful in the sense that it's been used to discover 3,000 of the currently 5,000 planets known today. It's probably actually more towards 4,000 planets that have been discovered using the transit method today. The other method that I use is the direct imaging method. And I'm not going to talk because we have this lovely video from Goddard that y'all made.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. A corrupting directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
I really love this video that your awesome comms team here at Goddard has made, because I usually put this in the middle of my public talks when I am just tired of talking. And I can actually take a break and have a nice sip of water But also it really distills direct imaging down into like a nice 2-minute video as well. And the joke I usually make is that's how direct imaging works, all by magic. And there'll be a pop quiz on this later. So it's pretty incredible that we're using technology basically from 200 years ago, because astronomers got impatient waiting for solar eclipses, and now we're using it for exoplanets. It's, you know, we have the DMs on board, the deformable mirrors, we have all this amazing post-processing, but really at its core, it's, you know, pretty old technology, which is pretty cool. Moving on, we're truly living in the sort of the golden age of exoplanet science, and it's really cool to be around at this point of you know, all this happening. We had this amazing groundwork given to us by ground-based telescopes that continue to push the boundaries. And you have Keck, you have the LPT, you have WIN, you have all these telescopes on the ground making these amazing observations, both of transits with RV, radial velocities, and also direct imaging. You have this amazing work that's been given to us by Hubble that's been doing this really nice look into the water abundances of a ton of these exoplanets. Spitzer, rest in peace, had all these amazing phase curve observations to give us longitudinal maps of these planets. Kepler and TESS have discovered hundreds, if not thousands, of planets to date. And then James Webb, you might have heard of that here at Goddard, I don't know. It's every paper that seems to come out is always nature worthy, which is incredible. You know, we're learning so much new things about these exoplanets. Every single bit of observations is transformative science. We're finally able to look at molecules that we've been predicting that should be in exoplanetary atmospheres the last 20, 30 years. Now we can actually finally see them due to James Webb's precision and also extended wavelength coverage. And, you know, those are all missions that have launched in the last 20, 30, 40 years in Hubble's case. And you know, are continuing to fly and test in James Webb and Hubble and do amazing science. But then looking forward beyond that, the future's super, super bright. We have this mission, Nancy Grace Roman Space Telescope, which hopefully all of you have heard of after walking through Goddard more than once, hopefully. Pandora is just being led out of here by Elisa as well. And then you have Ariel, which is a European Space Agency mission launching at the end of this decade. That's a mission that'll be doing spectroscopy between 5 and 8 microns to look at molecular abundances of exoplanets. And Ariel's really interesting because it'll look up to 1,000 planets. So James Webb gets us that really nice high precision observations of hopefully up to 200 planets. And then Ariel will be doing this for a statistically large sample. So it'll take the very high precision measurements of James Webb and place them into a larger exoplanetary context. And then looking beyond that, you know, we have HabWorlds, which is the amalgamation of probably LUVOIR and HabX. You have OST, which is living on kind of as Prima. And, you know, LUVOIR, HabX, now HabWorlds is explicitly being built to look for habitable Earth-like planets. And they'll be launching in the 2030s or 2040s. So it's kind of mind-blowing, honestly, that within our lifetime, the next 10 to 20 years, we'll finally be able to answer that question if we're alone in the universe, which is mind-blowing that I have a little tiny part of. So it's really, really cool. So first up, what I'll be talking about is sort of looking forward to the next immediate future, which is the next NASA flagship mission, Roman, which Neil and Tyler very kindly showed me back in the clean room, which was super cool. They did not let me in the clean room. They know better than that. So I did not get anywhere near flight hardware. Don't worry about it. But Roman Space Telescope, for those who don't know, is named after Nancy Grace Roman. She was NASA's first chief astronomer. She's sometimes called the mother of Hubble because she was one of the main proponents for getting Hubble launched. So in her honor, they named W first after her Roman Space Telescope. Same size primary mirror as Hubble, 2.4 meters, but it has 100 times the field of view because one of those spy agencies nicely donated to us. So rather than looking down and spying on your newspapers, it's now looking up, or will be in a few years. It'll do lots of cool science like astrophysics, dark energy, exoplanets, and I'm very biased. I'm from JPL and I work on one of the instruments called the Coronagraph. So I'm most excited about direct imaging, but it will also look through planets using the transit method and microlensing. And we're supposed to launch no later than May of 2027. So the Coronagraph really enables us, the Coronagraph on Roman. You can sort of think of this as a stepping stone. It's called a technology demonstration. So it's not like a pure science instrument in the sense that we have basically one requirement for the mission. And we have to demonstrate that on the 3 months that we're given within the first 3 years of the mission as well. So currently with ground-based telescopes, we're limited to this region up here. So things that are at relatively low flux contrast, where you have the flux ratio of the planet relative to its host star. And we can get down to 10 to the 8 contrasts, but we're typically around 10 to the 5, 10 to the 7. And that's including HST, James Webb, and ground-based telescopes, large ones like a Keck or Gemini. And typically the separation between your planet and your star is relatively far away. That's all well and good, but we really want to get down here is 10 to the minus 10 ratio and separations of 0.1 arc seconds. We want to see those Earth-like planets at 10 parsecs because, again, I'm a giant Star Wars nerd, folks. I want to ride the Millennium Falcon. To do so, I have to know where it's docked. Right, Tyler? Yeah. Yep, perfect. Tyler's a big Star Wars fan too. So in order to do that, we have to figure out where it's being serviced. And roaming chronograph is that stepping stone that gets us to where we are to down where we want to be. So the chronograph is going to enable us to get to flux ratios of 10 to the minus 9. It's a lot like looking for the light of a firefly around a lighthouse on the other side of the country. And what's really interesting about this is it'll enable us for the first time ever to directly image Jupiter analog planets. Jupiter-like planets and Jupiter-like orbits around sun-like stars. And again, Jupiter planets are well and good, but it's really to demonstrate the technology that we need to use to develop and to take all those lessons learned that we're making right now at CGI and then applying them to the next generation of those missions. So we just had a community participation program call that was just closed. Hopefully it'll be announced soon who's on the CPP. Giving Dominic some looks. Couple weeks, okay. We're all really excited about getting some new science folks involved in the mission and the instrument. And yeah, hopefully what we'll be able to do is, I'll talk about this in a second, we'll be able to demonstrate that CGI is the best thing since sliced bread, and we'll be able to get a lot more time on Sky and test out some of its other modes and do more observing as well. So as I mentioned, this is it's a critical technology demonstration. Direct imaging has primarily been done from the ground using very large telescopes and typically in the infrared versus the visible. So CGI will be operating more at visible wavelengths. And we'll be demonstrating a lot of these technologies for the first time ever in space. So we'll have ultra precise wavefront sensing control. We'll use large format deformable mirrors or DEMs. We have these high contrast chronograph masks. I'll show another photo of this later, but that's about the size of a quarter. So it's kind of interesting and incredible how big CGI is. I'll talk about this in a second, but also some of the small parts of it on its optics bench. We'll be demonstrating this low noise EMCCD electron multiplying CCD detector. We have to use these detectors because the planetary signal is so very small. We're getting like a photon like every minute, I think. Something's really, really slow, really low signal. So we need to eliminate as many noise sources as we can, including any noise in the detector. So you're using this electron multiplying that basically has this amplifier that reads out the signal and multiplies that signal to make the signal dominate over the read noise of the detector. And some really cool post-processing that my office mate Marie Goof works on a lot as well. So the chronograph itself will operate over 4 bands here. Band 1 is our TTR5 or our threshold technology demonstration requirement. So we have to do band 1 imaging, so photometry, in order to get those high fives from President Biden himself. Bands 2, 3, and 4 are other modes that are sort of goal modes, specifically bands 3 and 4. Bands 1, 3, and 4 are all being tested prior to launch, and we're working on making those test plans literally right now. Neil just sent me his draft on spectroscopy yesterday. Thank you, Neil. Beat the deadline by a day. Very nice. And band 2 will not be tested on the ground, but we're hoping to use all 4 bands when we're using CGI. Band 1 and band 4 do both imaging and polarimetry. Imaging is really interesting, obviously, because it enables us to look at the emission of these exoplanets. Band 1 specifically, you have some nice methane features. Polarimetry I'm really excited about as well, because it'll enable us to look at the polarized light of these targets. And that's really helpful, specifically these wavelengths, because it'll allow us to sort of poke at the molecular composition of these clouds and hazes on these exoplanets. And it made it, I would argue that knowing the what sort of molecules are in these clouds is one of the outstanding questions in exoplanet science today. So hopefully we'll be able to do that with polarimetry and also do some interesting disk science. There, Sarah.
Why are we not just doing two?
Because we just don't have time or money to do so. And as a tech demo, CGI does not drive the schedule of the mission. It's all WFI. So if CGI is late, the mission will fly without us. So it's best to not be late for the bus, for sure. And then bands 2 and bands 3 are both relatively low res spectroscopy, R50, but we'll be able to start resolving some methane bands. And I'll show you some simulated data a little bit later. And the spec mode has been built and tested by Tyler and here in the room. So thanks guys for all your awesome work. So here is our coronagraph. It's about the size of a baby grand piano for context. It's actually in the clean room at JPL right now. And I was always blown away by its size because I've always seen it in CAD drawings such as this online. So I had no idea how big or small it was. And then they actually let me go next to it and touch it, which was pretty cool, and see how big it is. But at the same time, it also has tons of very small optics on board and filters and coronagraph masks as well. So it's kind of this cool mashup of things that are pretty giant. You know, the telescope itself is the size of a semi-tractor trailer and very small optics that's been precision made and aligned as well. So here's the overall instruments. We have it's a warm radiator, thermal subsystems here. This is the main optics bench. All the interesting stuff happens with the light passing back and forth. It's 2 deformable mirrors, some focus control, some fast steering mirrors, all of its PAMs or its precision alignment mechanisms, which hold our filters, our chronograph masks, are all in the center here. I'll show you some photos of that as well. And then here's all of the hardware that drives all of that stuff on the optics bench. So here's a picture of the optics bench itself, just to show that it's something that's real. We're actually trying to call it the Roman chronograph instead of CGI. I'll occasionally slip up and call it CGI because, you know, computer generated imagery, people will think that this isn't an actual real mission, that NASA's faking it all the time and wasting taxpayer money. Actually, funnily enough, in the Astro 2020 Decadal Review, CGI is actually defined as computer generated imagery. So even NASA thinks, like, this is not real. I guess I don't know.
That wasn't NASA, that was
National Academies. Okay. Okay. So in order to prevent people from getting confused and thinking that we're just making CGI movies all the time in our offices, we're trying to name it publicly the Roman chronograph to prevent that sort of mix up there. But that's the main optics bench. It's in one of the high bays at JPL. Again, size of a grand piano. You can see an engineer working on things right there. This was taken right not too long after it was actually delivered to JPL last summer. So it's the optics bench is a bit more populated by now. You can see the 2 DEMs, or at least mirrors where the DEMs would be, are right here and right here. And I think these are just reflecting mirrors. The DEMs are probably off of the side optics table as well. And it looks like a lot of the PAMs are missing from here, but these are the photos that were cleared. So I have to show you these. But here's the overall chronograph architecture. I'll be stepping through this with some really cool photos just to prove that CGI, the chronograph, is real and it's on schedule and being built. We're actually gearing up for TVAC and full functional testing this fall. So we'll be doing air testing in, I think they're saying September, October, and then we'll be doing TVAC testing in November, December, and January, and then delivering out to you guys in May of next year. So it's right around the corner, which is super scary.
So where in here do you, what selects that you can only do imaging and polarimetry in band 1 and 4, right? Which are like the shortest and longest wavelengths. So it's not obvious to me how that selection gets made.
And that's in the DPAM. So we have the imaging masks here and also the polarizer prisms as well. And then also the spectroscopy ones in here too, that Neil and Tyler are working on. And we have our color filter. But then we have chronograph masks that are explicitly designed for each imaging mode. So here's band 1 right here. So we have that pupil plane mask in our SPAM or SPAM with the specific focal plane mask, the Leo stop, the field stop, color filter, that's band 1. And then we have a reflecting, basically as a reflecting mirror. It looks like my image isn't paced properly in here, but that should be like a little, just basically a mirror for that.
So they can all be moved independently. It's just that they're designed to work together as a system in one band versus them.
Exactly. So each of the masks have been explicitly designed for that wavelength and that mode. So you really can't combine the direct, band 1's pupil plane mask with band 4 or band 2 spectroscopy. Each of them explicitly designed for those wavelengths and the field of view as well.
Could you combine polarizer with some of the spectroscopy things?
No, I don't think so. Oh, Tyler says yes. Okay.
Yeah, absolutely.
All right,
Awesome. You could, it's just a question of whether or not you get the field of view from that particular chronograph that is in those modes. It's not a baseline configuration profile, but the polarization prisms are fully broadband across the entire CPI band. Yes, that was part, by the way.
Thank you, guys. Yeah. Might be fun in the future.
Thanks, Neil and Tyler. Yeah, so the question in the room was, can you use the poll on the other bands such as bands 2 and 3? And the answer from Tyler is yes. So thanks for being here, Tyler. Here's our fast steering mirror, our FSM. This is to help place, it has these actuators behind it. It enables us to place with high degree of accuracy a star or any other object on the focal plane wherever we need it to be. We're actually using this for flat fielding because CGI does not have a flat field lamp. So we had to basically use an astrophysical source, Uranus or Neptune, to act as our flat field lamp to make flats. That was a fun year to work on that. Can talk more about that a little bit later if you like. Here are one of our DMs. I think this is DM2. So it's a very, very thin mirror. And there's a bunch of actuators or little pistons on the back that help us move and change the shape of that deformable mirror. And that allows us to correct for any aberrations of light. While we try to make things as perfectly as possible on the telescope, nothing is perfect as it could be. And this helps further correct out any little aberrations of light within the optical beam train as well to get us higher precision. So to the best of my knowledge, DMs have not flown for direct imaging missions before. So this will be the first ever test of this on sky. So this will be pretty incredible to turn those on and to dig that dark hole to get that high contrast region to start taking observations of dimmer objects. And it takes about a week for these DMs to stabilize. So very, very precise hardware on board for sure. Go here. Come on. Here's one of our pupil plane masks. So this is our PAM right here, our precision alignment mechanism. And this moves both in the X and Y directions. And so you can move each of these masks in and out of your beam. So you can see each of these designs are specifically made to cut down any interference of light in itself. So you can see right here, this pattern, there's the secondary mirror of Roman, and then there's the spider support system of the secondary mirror to block out any aberrations of light around that. Here's
the precision on it, and what's the tolerance?
That's a great question. I think it's width of a human hair, if I remember correctly. That was made by JPL's micro devices lab. So that was actually printed right down a building across the street at JPL. And that's about the size of a quarter, each of those little masks. So very, very small. I don't remember the exact precision though, or the tolerance on those. Maybe Tyler remembers. There you go, 5 microns. You just want to give the rest of the talk, Tyler?
Is that the tolerance on the placement of the mask, or is that the tolerance on that shape? That's the optimized pixel size. But they when they run the optimization, the plate scale, they're doing optimization. If you look at under a microscope image of this, you'd see little squares. They're little squares that make up the mask. Yeah, I see. And how well can you place that?
Yeah, exactly.
Into the beam. What's the tolerance on that? So it's repeatability. It's a similar number. There's 2 stages to it. So there's a core stage. You can see like the 20, 30 micron rate, and then you lock in like 5 micron. The precision of the encoders is better. Yeah, that sub-micron measurement capability of actual fit where you end up landing. Yeah, kind of jump around. Yeah, whatever. Yeah.
Yeah, so those who are online, in case you didn't hear, these PAMs have you can command them to go to any position within 5 micron precision, which is extremely helpful. It's actually really great because we don't have to worry about it too much in our error budget, which is super helpful. It's nice not to have to worry about certain things because you have other things to worry about all the time. Here's an image of our focal plane mask, our FPAM. You can see all the little holes where light can come through. And these are all different wavelengths and modes that operate on the chronograph. There should also be some alignment keys. There's like a little T there, or like a little arrow as well. Our Leo stop or LSAM, you see it's a little hard to see from this image, but there are those patterns right there. You can see the cutouts from the secondary mirror and the region to obscure the star's light as well. Here's our field stops, our FSAM. We have a variety to choose from as well. It's really incredible how tiny all this stuff is on this grand piano or baby grand piano of an instrument. And then here's our pretty color filter image. Have to always show this because it's just looks cool, all the lighting back there. So those are all the various color filters we have on board. We have those 4 main bands. We also have sub bands for engineering that we use to help us dig the dark hole. And we could also use them to do other interesting science perhaps as well. And then here is our dispersion or polarizer DPAM. So I believe those are our 2 imaging lenses here. Here's some Amici prisms that Neil and Tyler have worked on for spectroscopy. And I think here's the Wallistons for polarimetry as well.
And they're all on these 2D articulated things instead of wheels.
Yeah.
Why that design choice?
I don't know why the design choice. Do you?
I know, but it's.
Oh, go for it, Tyler. I'm happy you're here to answer this
So-
question.
So, I mean, the very historically, when they were working with MPI, to make the mechanisms and provide them, JPL wanted them with U wheels.
Mhm.
We kept asking for that. There's a wheel and an X stage. And they finally came back and said, well, we're either gonna make them XY stages or we're not gonna make them. And we, XY stages are great.
Okay.
It kind of saved us a little bit operationally, interesting, though, because some of our con ops and stuff we had to do to compensate for some of our tolerances and stuff through the system wouldn't have been as quickly achievable with a wheel.
Mhm.
So
I mean, it looks way more compact.
the wheel actually would be more space efficient.
Oh,
Yes, because you don't change your footprint in one axis, it just rotate and then slide, right? So that was actually the reason for the complaints, the volume footprint of the XY stage is a little larger, so it's difficult to accommodate them. But the slit spectroscopy mode would not have been possible, really, if we had not had XY stages. So that actually was a downstream major bonus. Yeah.
Those XY stages, I mean, I assume that they're a done deal and have been used before.
That was why they wanted to make them XY stages. They had a high heritage in that fabricating something that hit the tolerance.
Yeah.
No, cool. Obviously, I'm a scientist, so not an engineer. They very wisely do not let me get anywhere near flight hardware. So now you see why. So yeah, I forgot to mention I'm on the project science team on CGI, and I'm the SciCal science calibration lead. So I work mostly on my laptop all the time and not by flight hardware, which is the right decision, honestly. So thanks, Tyler, for all the help. Here is the back end of our EMCCD as well. So there it is right in its electronics. And so while the chronograph is a technology demonstration, we do also hope to achieve a lot of science with it. And this is some of the science that has been sort of pulled out by our science investigation teams, our SITs. And this weird dude up here, Neil Zimmerman, you might have heard of him as well. It's going to be really interesting, though. We'll be able to look at the methane content of these exoplanets as well. We'll be able to look at the reflected light, their own emitted light if they are super self-luminous and young. We're going to be doing probably a lot of interesting disk science as well. And then looking at the actual orbital solution and mass measurements of these planets, which is pretty incredible. I sometimes show, or I always show when I give public talks, that awesome animation of HR 8799, where you can observe the planets, the 4 planets orbiting around its star in real time over 7 years. And hopefully we'll get long baseline observations like that with CGI and be able to actually watch extrasolar solar systems in real time, which would be pretty cool.
Do you know what system is being simulated here?
What system is being simulated here now?
That was the fictitious system for the data challenge, but it could resemble something like 47 Numa, where there's 2 or 3 gas giants that are in a pretty short period. orbits.
Yeah, and actually target selection for CGI is something that's being thought of, or will probably be thought of sooner once we get the CPP call done and get those new teams in. But right now we're all focused on INT and testing this fall. But yeah, so the question of what targets we'll be looking at CGI is still an outstanding question. Also, I run these Roman virtual lecture series. So if any of you want to give a talk on your research or work that is related to Roman, be great to have you. Dominic gave a great talk about Nancy Grace Roman herself, which is really awesome. So I think Tyler, you gave a talk too, right?
I don't know if I did one at the Roman virtual.
Well, now you're gonna be signed up. Congratulations. You've been voluntold. So you can scan that QR code. We haven't had one yet because we're waiting for the CPP call to come out. And also we've just been slammed with everything else. So we'll hopefully start this up again soon.
Yeah, there wasn't one yesterday.
There was not one yesterday. I was also en route from LAX to DC. So that's about all my work on Roman CGI. Another project I work on at JPL is Exoplanet Watch, which is a citizen science or a community science project to observe transiting exoplanets. And, you know, while we looked at all that exciting work you can be looking forward to and all those observations from direct imaging, and honestly, that looks like that's the direction the field is going into. You know, looking at the astrodecadal report, it was mostly about direct imaging to look for potentially habitable planets that are Earth-like. But the transit method, I argue, will be here to stay. Next generation missions will likely be using this method to look for biosignatures potentially on planets. But also more immediately, Hubble's looked at tens of planets and done a nice cataloging of the water content and the cloud presence and haze presence on these planets. James Webb is going to be, already has looked at tens of planets and probably will look up to 200, if not more, exoplanets as well. Ariel, that European Space Agency that I'm on the science team for CASE, which is a contribution to Ariel, that'll be looking at up to 1,000 exoplanets. And it will place, again, those James Webb observations, those very high precision observations, into a larger statistical context. So the transit method I argue, is still here to stay. And at least right now, it's immediately extremely interesting. We're learning a ton of information about exoplanets today. But if we want to use a James Webb or a Hubble to observe these planetary transits, we have to know very precisely when they will occur. So if I write a proposal to the telescope allocation community committee for James Webb, and I say, hey, I want to observe this planet, I have to give them an accurate transit time to schedule the telescope on. If there's a 5 or 15 minute uncertainty on that transit time, that's an extra 5 to 15 minutes I have to build into my overhead. And while that doesn't sound like a lot, you know, about an hour of James Webb time is worth about $100,000 to $1 million, depending on how you count. So you want to save taxpayer money. Also, anytime you're waiting for these things to occur, that's preventing other interesting science from happening as well. So, and then that problem is even further compounded when you start looking with Ariel, because 5 minutes times 1,000 planets is quite a lot of time you're wasting. So you can either build an observational overhead, or you can then, you could also instead do ground-based observations. So I was working on this project called the Micro Observatory and helping them out a little bit. This is a small telescope out in Tucson. It's like 6 inches across. But it's a robotic telescope that observes every single night, rain or shine. It's actually fully weatherproofed. And I was looking at this data of HAP-P32, relatively dim star, 11th magnitude, you know, about 2 to 3% transit signal. And I was really blown away by the data quality. You know, you can use this telescope that was built in the early 90s to get very high precision observations of this planet. And roughly the same time, I was giving public talks and I had amateur astronomers coming up to me and saying, hey, what you're doing is kind of interesting despite all your bad dad jokes. Is there any way I can help out? And that sort of got me thinking that there's a ton of amateur astronomers out there. There's not enough professional observatories that we can use to do the recon work that's really needed here to update these transit times and to look at these targets. So why not get the amateurs involved? So we did this study in 2020 that looked at the capability of small telescopes specifically. For example, on the left was the known planets at the time. And this was about 4,000 planets. And a single 6-inch telescope in one night of observing could observe about almost 200 targets. So any given night, basically, a single 6-inch telescope, which is a run-of-the-mill telescope for most amateur astronomers, could do really impactful science on a large target set. And you can do that for planets that have transit depths typically down to about 0.5%. If you're lucky, more so 1% is more of your sweet spot there. And these are planets that have very uncertain mid-transit times. And then if you took this a step further and you said, okay, let's try to observe all the targets we can get using a single 6-inch telescope. A single 6-inch telescope can save on the order of about 10,000 days of observing time. And that's just because a lot of these transits are very unknown to date. And a lot of the observations, a lot of the mid-transit times and orbital periods on the NASA Exoplanet Archive are from a few years ago. Some planets haven't been followed up in a while. And you can use small ground-based telescopes. You can use TESS as well to look at these transits, update their timings, and then save us a ton of time. And if we had a single 6-inch scope, we threw out these outlier planets, we could still save up to about 10 days of observing time. So if NASA wants to cut me a $10 million check, I won't say no. But even if we have a very modest observing group of about 16 6-inch telescopes, which we can easily do today, we actually have over 1,700 users in our project, you can save about 100 days. So $100 million, NASA, that'd be great. I'll settle for 10 million if that's all right too. We can also do a lot of interesting ancillary science by just looking at these photometric transits as well. We can look at something called transit timing variations. We can look at the transit time, see how it varies from epoch to epoch to see if there's additional planets in the system. So normally if you have a single planet system, it orbits around its star at a predictable clip, like every 3 days, and it'll happen every 3 days on the dot. But if you add a second body in that system, the gravity of that outer object or the inner object will cause the planet's transit to vary back and forth. And you'll get this sort of sinusoidal shape of the mid-transit time. And then from this, you can actually get mass measurements, and you can use it to discover new planets as well. And a lot of this is afforded to by our very large baseline of observations, which we include observations from our observers, as well as from the archive. And then from our data, we actually have 10 years of archival data from the microobservatory alone. So we can actually start placing limits on other planetary companions in those systems. We can also importantly monitor stellar variability. So here's some data from the APT, the Automatic Photoelectric Telescope of HD 189733b. This is one of the brightest transiting exoplanets known to date. It's about a 6th magnitude in V and about a 2% transit depth. So it's a great target to look at. Unfortunately, 189 is a very variable host star. And the question worry was, does the variability of the star impact the observations that we're making? Because whenever we're doing transit observations, our data, our measurements are always flux of the planet relative to the flux of the star. So if the star changes, that could potentially impact the planetary signal that we're looking for. So here's a study that we did back in 2019, where we took that APT data and were able to analyze the activity of the star and confirm that it did not likely impact the eclipse observations we were making. And we can easily do this with Exoplanet Watch, our network of small telescopes as well. They can get, I think, a percent precision in a single minute exposure. So you can get very high precision observations as well. And this data can then help us better understand and interpret high precision observations that are being made by James Webb. And stellar activity is very, very important to understand, particularly by James Webb, thanks to its high precision that's afforded to us by this time. Hubble, we could kind of sweep it under the rug a little bit, but James Webb, it's very important to understand and to characterize. We can also look for blended pairs. So TESS is an amazing instrument. It's discovering tons of exoplanets. And it does that wide field view of the entire sky, or at least a nice big slice of the sky. One sad side effect is that it has very large pixels, about 21 arc seconds across per pixel. And what can happen is if you look at an object, you can actually have two blended as a single object. So here's actually a sample image from the Micro Observatory, a 6-inch telescope, which has 5.21 arc seconds per pixel, so about a factor of 4 better spatial precision. And here you can see one star, and then there's a second star nearby. The reason they look like potatoes is the Micro Observatory tracking isn't perfect over this minute exposure, so there's a little bit of smearing. But regardless, you can still see that there are 2 stars that get convolved into a single pixel here on TESS. And the reason why this matters is because that second star can dilute your exoplanet transit signal. So a planet that you could think is like a Neptune-sized planet of TESS could actually be a Jupiter-sized planet or even a brown dwarf in actuality because of that blended pair. So given all this cool ancillary science we could do, given this need for updating transit times, we launched a few years ago Exoplanet Watch, which is our community science project to monitor transiting exoplanets. So this is a collaborative effort to complement existing surveys. We're members of TFUP, SG1, and the Single Transitors Group. We're very collaborative with Exo Watch, which is like our Exo Clock, which is like the European version of Exoplanet Watch that is monitoring aerial targets. All of our data is immediately public. There's no proprietary phase, so you can go on our website right now and scoop us. I hate writing papers, so please do. We also have target requests by professional astronomers. So if you have an upcoming James Webb run and want us to help observe some targets for you, and I think we'll be doing this for Pandora as well, we are more than happy to. And our observers love helping out space observatories and also other professional astronomers. All of our observers are listed as co-authors. If they do the work, they deserve the credits. And we're funded fully through the end of 2026, at the very least, by NASA's Universal Learning, which is PI'd up at SpaceTel. Given that we're a citizen science project, we have educational and science goals. Science goals I went over, ensuring the efficient use of large scopes, discovering new planets, monitor for stellar variability. But our educational goals are to engage and teach the public about exoplanets and enable them to do science. Really, it's to inspire the next generation of STEM learners to hopefully have them go into astronomy or similar related field as well. So if you're interested in joining, this is sort of the roadmap that you can follow to participate in this project. You can actually fully participate if you have your own telescope or even if you don't have your own scope. Let's pretend though that you have an observatory lying around and you want to get involved in our project. You can go on our website and you can plan your own observations. We have this lovely plugin through the Swarthmore Transit Finder that'll tell you whatever target is observable from your local neck of the woods. They also have our target list on there as well. That being said, we'll accept observations on any transiting exoplanet. We don't care, just give us the data. That's all that really matters at the end of the day. But we do have a metric that we use to prioritize targets for observation. And then actually here's Brian observing with his, looks like it's a 14-inch or 16-inch telescope out in Montana as well. If you don't have your own scope or don't have access to them or have June gloom like I do in SoCal right now, you can actually request data from us. We are very lucky that the Micro Observatory right here has been observing planets, transiting planets the last 12 years, and they've donated to us over 2,000 data sets. So we've been able to farm this out to folks who don't have their own telescopes to analyze as well. And actually what I'm working on right now, getting 2 telescopes set up. I have a 0.4 and a 0.6 meter at Table Mountain, just northeast of JPL on the way up to Vegas. So I can do some gambling and do some observing maybe in the same day. And we'll be having those 2 routinely, robotically, fully automatically observe transiting planets as well. I have access to a 1 meter during bright sky time, so about 2 to 3 weeks a month. And I'm looking at making an array of 6 6-inch celestrons up there as well, the roll-off roof. So perhaps we'll have at least 8, maybe 9 telescopes out in Southern California doing observations. So if a professional astronomer comes to me and says, hey, can you observe this target? If it happens over SoCal, I can guarantee, as long as it's not cloudy, that we can get observations on that target, and we can activate our users as well. Once you have your data in hand, you can then analyze your data. I didn't want this to be a black box experience where people upload their data to a server anywhere. I wanted them to actually have that full participation in the entire data analysis process. So you can use whatever analysis tool you want. A lot of people use Astra ImageJ. There's also Hops from Exoclock. We've made our own called Exotic, I'll be talking about later. But importantly, these folks are using real tools that professional astronomers use to analyze their data. So they're really fully participating as a scientist here. They then upload their data to the AAVSO, the American Association of Variable Star Observers, to their database. This is actually an awesome partnership. We have the AAVSO. They're such a giant, awesome group of folks to work with. They have tons of astronomers across the world. And also the timing of this was really great. They just happened to launch this database right when we were trying to figure out how users could get their data back to us. Because for some reason, JPL doesn't like members of the general public uploading data to JPL servers. I don't know why, go figure. So this actually saved us a lot of time and a lot of effort. We were thinking of doing some convoluted thing of Dropbox. So this is a lot better. So people upload their data to AVSO's database for free. And you can kind of sit back, relax, get published. We're actually working on 4 papers right now with some interns, which is great. They'll be leading them as first author papers. And then we'll have a ton of amateur astronomers on there as co-authors. I mentioned Exotic earlier. This is our Exoplanet Transit Interpretation Code, and I actually presented this at the CE's data tool workshop that happened a few months ago. So thanks for having me virtually on that as well. This is our real astronomy analysis tool. So this is exact code that I use professionally to observe my own transiting exoplanet data. And this is the code I actually use to analyze everything that we use for transits for photometry. It works on any telescope, regardless of the platform. And it works in as fast as about 4 minutes. So it does your calibrations of your images, flat stark biases. It picks out your optimal aperture size, your sky annulus size, picks out your best comp star. It also fits your data using a nested sampler with an actual model transit light curve. So it gives you full posteriors. So literally you point out your FITS files, and then 4 minutes later, you get science grade light curves. I can say that because we used Exotic to publish these light curves in 2020, and full posteriors as well. So you can give it actual realistic uncertainties in all of your measurements. This runs either locally on your own computer. You also have it
operating in the Google Colab cloud.
And fully participate in this project using just a smartphone. So you don't even need a nice computer to operate the software. We also run Exotic on our own servers as well at JPL. We are always scraping data from the AAVSO's database right here. And we scrape it about every other day. We reanalyze, reprocess the data using a slightly tweaked version of Exotic. And then we immediately publish them to our website as well. So there's a lot of back-end work happening as well. But probably most interesting to this group is our observing campaign that we did in December of 2021. And this is to support some observations of HG 80606b on James Webb. Tiffany Katari at JPL is the PI for this observing campaign on James Webb. And I think it'll be scheduled hopefully for this fall. And they're observing this target, but it has a very long transit duration, about 12 hours. And in transit observations, you also need to get out of transit baseline as well. So that's about a 14-hour transit observation window that you need to hit. So it's physically impossible for a single person anywhere in the world to observe the entire transit. So what we did is we basically simulated a very large worldwide telescope. We had a bunch of folks starting their observations in Japan here, pass it over to folks in northern India, to Eastern Europe. I think that's the Canary Islands out there. And then back to the West Coast of the US, and then back to Japan again. And we're able to stitch all these light curves together to make a single light curve. We had about 24 facilities participating in this project, all small telescopes under 0.7 meters. We probably had another 30 to 40 folks that were interested in participating, but of course, most of the Northern Hemisphere was cloudy that night. I remember looking at the cloud maps and just freaking out. But luckily there were some clear holes that folks were able to observe. We probably had a bunch more folks in Western Europe and a ton of folks in the East Coast, which is cloudy that entire night. And so it really shows why a worldwide distributed group of folks is needed, so you can overcome things like weather, or you can simulate a large global telescope to get you these large observations. And looking at the individual data quality, they look okay, right? You might see a transit, part of a transit there, scatter looks kind of big and flat. Sure, on an individual basis, the data doesn't look great. But when you start phasing it together, you actually get a really, really nice light curve detection. And some of our individual users are actually able to get within a factor of 2 to 3 times the precision of tests. And those are actually done by some of these EV scope folks. Those are 4.5-inch telescopes. They have about 10,000 worldwide, which is crazy. And we were able to phase it all together and get this really nice high precision measurement of the transit. So if God forbid tests were to blow up tomorrow, hopefully it won't, for obvious reasons, we could still do really transformative science from the ground using the amateur community as well. And from this data, and we also combine it with tests and RV measurements, we are able to greatly constrain both the transit and the eclipse times of this target. So here are some previous transit measurements from our campaign. You could see here, this is the 1 sigma region of uncertainty of the next mid-transit time. What happens is the next predicted mid-transit time always gets more and more stale or more and more uncertain with increasing time. So the errors continue to compound and get larger and larger, hence that opening window. With our observations, we were able to whittle that down and save a few minutes on the transit, but more importantly, on the eclipse, we were able to save a bunch of time. And in total, we were able to save about 3 to 4 hours of observing here, just by combining the ground-based telescopes from the amateurs with tests and with RVs. So if you're interested in getting started here, this is a great project for students as well. We actually have folks as young as high school students writing their own papers and getting them peer reviewed as well, which is crazy nuts. But there's also tons of folks across the US, for example, that have small telescopes. You only need like a 4-inch telescope to participate in this project, even 3.5 inches. A motorized mount and a relatively cheap camera. We use these $200 ZWO cameras actually for our 6-inch scopes. And they're actually able to get really great observations as well. So you can scan that QR code or go to that website. I'm horrible at memorizing QR code patterns. So you can alternatively just Google NASA Exoplanet Watch and we should be the first thing that pops on up. So I know we went a little over, sorry about that. We also started a little late, but if anyone has any questions about the Coronagraph or Exoplanet Watch, happy to take them. Thanks again for coming and thanks for calling in. Appreciate it.
Ask a real quick question. That's a great talk. How do you ensure that data is calibrated properly when you're in citizen science data?
Yep, that's a great question. And that's where you use the strength of numbers play as well. So we're trying to push for as many observations of the same target as possible. And we can then filter out, dubious data. So here on this plot, you'll see we actually didn't include these data points in our analysis because the uncertainties were so high. So we actually threw them out. And we do use that we do basically a sigma clip there to throw out potentially dubious data. The calibrations actually, surprisingly, you don't need to do a lot of cals.
So you're hoping that the random spread of different people's data is not all impacted by the same systematic.
Exactly.
But you have 10,000 EV scopes, right?
There's 10,000 EV scopes, about at least 1,000 of them said they want to do citizen science. And we have usually 20 to 30 folks that are participating in our campaigns. So, and then everyone else is using very, very different telescopes. Different sizes, different instrumentation mounts. So it's, the common mode astrophysical signal is a bit easier to pull out from that as well. So it actually helps that people are using different systems.
Exactly. Yeah.
The micro observatory data, this actually has 0 calibrations applied to it. This is just the raw data, no flats, no darks, no biases. And despite that, you get a really beautiful light curve. That's very high precision. But then, looking at our O-C plots here, we can pull out data points that might be a little dubious. And, if you were to look at this at face value, you might see if there's a periodic signal there or a TTV, you can actually remove those signals as well. And actually, we'll be having a campaign on July 3rd of HD 189733B. I'll be asking everyone to do observations of that target because it's big and bright and easy to hit. And I'll be basically doing that as well, is to use that as a validation for our pipeline and our tools to make sure that I haven't put a bug anywhere, for example, in the code. Yeah. No, very good.
Follow up on a
Thanks.
question quickly. So if you go to this slide 43,
Mhm.
so those are all the individual qualitative photometric measurements.
Yep.
For 80606.
Yep.
And on the next slide, you show them all sort of stacked up together. Did you have to do any, like, I don't know, I'll just. So this greenish data set, no, this greenish data set here is down toward the bottom of the transit.
Yep.
And this magenta data set here is up slightly out of transit.
Yep.
If you go back to the previous slide, did you literally just take them from here and put them all on the same scale and it worked?
You had to do some scaling in some
Very
cases.
systematic
Yeah,
scaling.
because the reason why you can't just copy and paste them all together is they might be using different comparison stars.
I see.
So the flux might be a little bit different from target to target. So we do use the predicted transit shape as a guide to help us shift the data up and down.
Okay.
And that shifting is also included in the uncertainties at the end of the day. So we try to be as conservative as possible with all of our uncertainties, such as that vertical shifting where needed. Because otherwise, if you had, just like you said, this observation was in transit barely, but it doesn't look very different from the out of transit portion here.
That's what I was wondering.
Yeah. So ideally, you can help combat that by having overlapping data. So like right here, you have other data sets to help sort of anchor themselves down. But you have to use a vertical shifting in other places as well.
Okay. Follow on.
Yeah.
What you referred to is using different calibration stars. Now, I assume that most of these amateur astronomers have reasonably big cameras, scale cameras. So presumably there are a ton of 13th magnitude stars that are not particularly well resolved. You've got lots and lots of them. Do you actually just use a calibration star, or do you bootstrap the entirety of every star in every field every time?
So I actually do not like making a combination of comp stars personally, because so some groups will use basically like a giant matrix of different comp stars and have different weighting factors for each of them, and then use it that way to make a synthetic comp star effectively. I don't like that personally, because one of your comp stars could be variable and you might not know, and you might get introduced systematic errors into your light curve at the end of the day, and it's more difficult to figure out where that systematic might be coming from. So we prefer to do a single comp star here. For this campaign, we did have a recommended comp star that everyone used, but we don't enforce that. So if someone gave us data using a different comp star, we'll still accept it because we want the data there. We do, through our partnership with AVSO, they've actually identified comp stars, recommended comp stars in about 200 of our fields. And they've gone through and they've verified that those comp stars are nice ones that are stable, that are non-variable as well, to help us with this. But sometimes we just have to take the field that we can get for that as well.
Wouldn't the exotic pipeline that you described pick the comp star for them in a way? Couldn't you just take over that step?
Yeah, so Exotic does, if you're looking at a field and there happens to be an AVSO comp star in the field, Exotic will pick that up and include that in the batch of comp stars to use. And then the user-defined comp stars will also do a scrape against Sinbad and Gaia to make sure they're not variable as well. We didn't want to automate completely everything because we wanted the users to still participate in the data analysis product. We could conceivably make this just dump your FITS files here and run it fully automatically, but we had to toe the line between automation, but also participation as well. But yeah, Exotic does basically automate a lot of it for them. So this is sort of to answer his question a little bit earlier. A lot of folks, majority of our folks, if not all of them, use Exotic because it's just, honestly, it's really user-friendly. You can just watch and go through a little Google Colab tutorial, everything run in the cloud, you don't have to download anything. That was the biggest hindrance, was getting Python packages installed on people's computers, which is a nightmare. And it runs super quick as well. I think it's the fastest transit software on the market today, and it's free.
There's no question there, so I'll ask another one.
Yeah.
So it sounds like you have a bunch of people in this group who listen to what calibration star you want to use, who have telescopes that are well characterized,
Yep.
and who repeatedly provide observations. Have you done sensitivity analysis to look at, can I detect secular variations in orbital parameters for certain systems?
Yeah, that's what we're literally working on right now, is looking at for variations of the systems. So on our website, if you go to it on our results page, we're going to be launching O-C plots on there, and also be phasing the light curves as well to start looking for potential other objects such as TVs. We also have employed on our backend Lomscargo analyses as well to look for variability. And that's the goal, is to start looking for orbital evolution and orbital decay on these targets. So if you have a target you want us to look at, I'd be happy to get a campaign going and get our users excited about that. But updating the system parameters is our next big goal. Exoclock has been doing amazing work of updating a lot of these transit times. And what we're now trying to focus on is not only updating the transit times, but the system parameters as well to help better interpret James Webb observations. Cool. Any other questions, comments, concerns? I got stickers if you want them. Well, CGI and Exoplanet Watch. Stickers. All right. Any questions online? Also, if you want to, you can just email me directly if you have any other questions or think of a question later. You can just email me there or zellem@gapl.nasa.gov. All right, everyone. Thank you so much for your time. And thanks to folks who called in and also came out to the room in person. Really appreciate it. Thanks again for having me.
That's a crazy question. So you're gonna have things pretty far apart in this group. But when we look at things in the morning and night, we're gonna be crazy, like, what is it? And what's my parallel path? What's my all these other things that I can do by the spatial?
Not yet, but there's definitely a lot more things we want to take a look at, such as that. So the campaign that we did in 2021, there's some stickers if you want them. Sorry. And also CGI stickers too. Yeah, I brought another stack of those for CGI for tomorrow. Exoplanet Watch, probably not though. We're low on stickers. Right. So the campaign that we did back in 2021 is something we've actually been wanting to do for the last decade or so. We've always wanted to have at least 2 telescopes observing the same target simultaneously, because that way you can better analyze the systematic errors and pull out the shared astrophysical signal. So doing this for 80606 was honestly a dream come true for us. We've been wanting to do it for a while, and now we want to keep on going. That had been the longest duration transit ever observed to date in this global campaign, I think. And then 2 months later, they beat it. They had a 14-hour transit duration as well. So it's pretty cool, and the science we can enable from this.
Thank you.
Okay, guys, thanks.
Yeah, I'm
Yep.
upstairs. I finished directly above.
Perfect. Thank you, Sarah.
Yeah, all right, so we'll do lunch now, so everyone just told you any questions. But no, that's awesome.
So I can anecdote.
Yeah.